Hi, and welcome to the first of several lessons on stoichiometry and limiting reagents. So we'll start off today just with stoichiometry, a little background, a little bit of what it is, and then in the next video we will look at some example problems and exactly how we work through stoichiometry. So before we really get into the chemistry, let's just have a little example that has very little to do with chemistry. So we'll look at this small example here to demonstrate a little bit about what stoichiometry is. So let's say we want to build a robot, and of course, with our robot we're going to take over the world. So if this is our end goal that we are trying to make, we're going to need some parts for our robot. Let's say we need an arm. And, since our robot's going to take over the world, we probably want 4 arms, right? Because no robot with 1 arm is going to take over the world. We also need some other parts for our robot. We need some circuit boards. Let's say 2 circuit boards. If we are using this robot to take over the world, besides arms and circuit boards, it's also probably going to need a cool-looking chainsaw. And, to go along with this cool-looking chainsaw, we're also going to need a flamethrower. And the last and most important thing, if we're going to be building a robot, is it's going to need a heart and it's going to need some love. So in this little equation here, we have 4 arms, 2 circuit boards, 1 chainsaw, 1 flamethrower, and 1 heart makes a single robot. Now, if we were trying to make 2 robots, right, having this equation, we would be able to figure that out. We would need 8 arms, 4 circuit boards, 2 chainsaws, 2 flamethrowers, and 2 hearts. Pretty simple, right? This is the basics of stoichiometry, that we have an equation with a certain amount of things that make what we want. And we can figure out, given the amount of things that we have, how many of our products we can make, or how much of our products we want, we can figure out how much of our materials that we need. So, as for a definition, stoichiometry is a system based on the laws of the conservation of mass, definite proportions, and multiple proportions that allow chemists to make predictions about the amounts of products and or reactants in a chemical reaction. Now, laws of conservation of mass, definite proportions, and multiple proportions we did talk about when we talked about the history of chemistry. There were several fine bearded gentlemen in the history of science that wrote these laws. You can look them up and review them at your leisure. So how is this even useful? So like I said a little bit when we were talking about our robot, there are several things that stoichiometry will allow us to do. One of those is that it allows chemists to predict how much of their products they can make based on how much of the reactants is available. Like, let's say we want to know how many rubies we can make. So we know we have a certain amount of aluminum oxide and chromium oxide, and we can figure out how many synthetic rubies that we can make. Another thing that is useful with stoichiometry is it allows chemists to figure out exactly how much of their reactants will be needed to make a desired amount of product. Like, let's say we know we need to make 2 tons of steel. We'll need to figure out how much pig iron we need to make that 2 tons of steel. Another way that stoichiometry is useful is allows chemists to figure out exactly how much of one reactant will be needed to completely react with a given amount of a second. So let's say, you're in the lab and you accidentally spill some hydrochloric acid somewhere. You want to know exactly how much base will be needed to neutralize this acid spill so that, you don't have a whole bunch of acid sitting around on the counter in your lab. So now we're going to see a real simple example of how this works with chemistry. So in its simplest form, stoichiometry is directly related to the balancing numbers in a chemical equation. So given this chemical equation, it tells us a couple things. It tells us for every one aluminum oxide here, it reacts with 6 potassium bromides to make 2 aluminum bromides and 3 potassium oxides. So now it's going to allow us to say if we have a certain number of moles of aluminum oxide, say we have 2, we can use the information in this equation, right, our 3 moles of potassium oxide and our 1 mole of aluminum oxide to figure out if we have 2 moles, how many moles of potassium oxide we can make. Of course, we see pretty simple math. We can make 6 moles of potassium oxide. This is exactly how stoichiometry works. However, if you noticed in that last example, this might mean that we need to review some dimensional analysis. So let's remember, units can be cross-canceled across a mathematical operation just like numbers in a fraction. So let's work through this problem. We'll find out how many atoms of iron there are in 12.89 milliliters. So again, just like any of our dimensional analysis problems, we're going to start with what we know. Right? The problem gives us we have 12.89 milliliters. We are going to then find the density to cancel out our milliliters, which happens to be 7.8749. And that'll leave us with grams when we cancel out those milliliters. So then we need grams in the next step, all right, which means we're going to use the atomic mass, which for iron happens to be 55.845 grams. You can cancel out grams there. However, we're not quite there because we're in moles now. So we need one last conversion factor. Good old Avogadro is going to help us out with this. There are 6.02 times 10 to the 23rd atoms in 1 mole. So our moles cancel out. We're in the units that we want. And we end up with our answer, 1.09 times 10 to the 24 atoms. And so that is dimensional analysis. So thanks for watching. The next video will have several different example problems for stoichiometry, and we'll look at each type of situation that I talked about here. So see you in the next video.